So thank you for everyone coming, and thank you to Surgeon for organizing this, as always. Today, I'm going to be talking about formal methods, which is a pretty broad topic, but hopefully we'll get some good kind of map of the territory, as well as some of a practical example. So my name is Tannr Allard, by the way. For those of you who don't know me, I graduated launch school and capstone a couple of years ago. And this particular topic is something that's both a hobby of mine, but it's also helped me a lot in the field, especially when I was working in blockchain industry, where we're writing these programs that are very critical, securing some millions upon millions of dollars of funds. It's very important to make sure our programs are correct. And as we'll see, that's kind of the crux of the issue that formal methods attempts to solve. So I think when introducing oneself or being introduced to a new technology, this kind of why, what, how sequence is what I've come to settle on for myself as well when teaching myself something new and when explaining something. It's important to understand the motivation behind the technology prior to learning what it does, and then from there you can dive into how it works. So that's kind of the agenda for today. And why, I just wanted to start off with a quote by Leslie Lamport. For those of you who don't know, he's a Turing Award winner for his work in distributed systems and consensus algorithms. And he has a book specifying systems, which I highly recommend if anything in this talk ends up appealing to you. And he says that it's a good idea to understand a system before building it. Couldn't agree more. So it's a good idea to write a specification of a system before implementing it, because writing specifications, formal specifications, as we'll see, forces you to understand the system you're trying to build far more than you would otherwise, and far more than, and it also shows you just how little you understand it, and you may be mistaken in how well you understand it. So formal methods in general help answer questions like, is my understanding correct? So for example, specifications. It also helps answer questions like, does my approach fit my understanding, right? Is there some sort of parity between the approach I've decided to take and my understanding of the problem space at large? And then finally, going even more into the, diving even deeper into levels of abstraction, does my implementation fit my approach? So it's common to come up with, say, design an approach. And informal specifications are quite popular, right? We all, and you may know this from the PDEC approach taught in core, you come up with your approach to a problem before you implement it. But when you're doing that, when you're making that transition, there's always a risk that the approach that you outlined and the implementation you've actually created are slightly different. And those subtle differences, sometimes so subtle that you can't catch them without the assistance of formal methods, can cause big problems, especially in critical software. So that's what formal verification attempts to solve. Formal methods, attempts to solve, is it helps us build correct software. And you can kind of think of formal methods on one end of the spectrum and say just testing on the other end of the spectrum, right? Testing provides us with confidence in the correctness of our code if all the tests pass, right? But testing, first of all, suffers from the coverage problem. You don't know entirely if you're, you don't know what you don't know, essentially. And we can get into the the epistemological confusion of that. But basically, there's just that issue of coverage, and you don't just have to cover when you're writing tests particular modules. You have to really, if you want to be completely confident, every particular execution path. And as we'll see with formal methods, you can specify a system so precisely that this testing of every execution path is actually a formal method called model checking. In the industry, yeah, these are some places they're used. Hardware, for sure. There's always formal specifications and verification of your hardware designs. And in modern hardware, it rarely do the actual hardware designers actually work with hardware. What's happening is using hardware description languages that are amenable to formal verification and formal approaches, design chips and other components, and then verify their correctness, as well as other properties, such as performance properties. But we're not really going to talk about the formal methods approach to, say, performance properties today. Distributed systems is another one. I mentioned Leslie Lamport and the book Specifying Systems earlier. Leslie Lamport is known for his work in distributed systems. So that's also a huge one, because you may have encountered this issue before. If you haven't yet, you definitely will. Is when working with distributed systems, time is a really difficult topic. Every machine or participant in a distributed system has their own local notion of time, and things need to be in different operations could be distributed across multiple participants in the system, and the results need to be synchronized and agreed upon, and that's super tough. It's also popular in mission critical systems. So for example, you think about all the software that the pilot in the plane that you're a passenger on depends on. It'd be really, really bad if that software malfunctioned. And software like that typically requires the level of confidence that you need to have in certain software is higher than in others. And mission critical systems are one of those. So yeah, things like airplanes and other types of systems like that, cyber physical systems essentially, tend to involve formal methods. And then blockchain, which is the industry I'm most experienced in, has been booming with formal verification and formal methods the past few years. It's rare to see actually a popular project that is not exploring or has already utilized to a large extent formal methods. And that's because the code we write essentially secures millions upon millions of dollars. And just as a war story, so to speak, is I was working with a company to build out some new infrastructure, and they were a decentralized finance company using blockchain technology. And in the middle of working on them, so they were migrating their system to basically the system that is created by the organization I was working at. Before they were finished working with me and architecting their system, they suffered a hack and $25 million were stolen. Now, the specific type of attack is part of a class of attacks known as reentrancy, and they're very well-known attacks, yet still for some reason, developers continue to suffer from those attacks by writing code that's vulnerable. And so formal verification tools have emerged in the blockchain industry to try to avoid these problems. And formal tools would have detected this problem beforehand and prevented many users from losing, in some cases, their entire savings. Right? So blockchain is kind of a financial critical system in that regard. Now, it's actually more popular than you might think. This is a great article that I recommend reading to motivate the use of formal methods in practice, right? Because there's this whole thing about formal logic, abstract systems. It's fun from a theoretical standpoint, and it's fun to study. But a common sentiment is, well, it's too slow, too expensive. You require high levels of expertise, and that makes it untenable to use for most places. But we'll get into one particular tool that I think is great and I use in my own practice. But this is a great article. It talks about how some of the teams at AWS were able to use formal methods and basically uncover issues and correctness mistakes in their algorithms that were simply too complex, too many steps in the algorithm to track it down manually. And so they were wondering, why are we experiencing this issue? And they could not answer the question. So they thought, maybe formal methods can help, right? And it did. And they use a tool called Tla Plus, which is also developed by Leslie Lamport. And Tla Plus is quite good because it's rigorous and it gets the job done. It's built for practitioners. And even in this article mentions, even the junior developers on the team, right, were able to learn to effectively use Tla Plus within a few weeks. And for that reason, for its ease of use, its intuitiveness, developers love it. I will say that just because it's intuitive and easy to use does not mean that it's not powerful. It doesn't mean that things are being hidden from you. It's common in developer tools that things that are intuitive, they're intuitive because they're hiding complexity. That's not necessarily the case with Tla Plus. It's not that it's hiding complexity and providing the right interface for you. Rather, Leslie Lamport and some others made a decision, I'll talk about this more later, that the right way to do formal verification, especially in the industry, is to not use sophisticated things like type systems and just use elementary math instead. And so that's what happened. I'll get into more of that later. So formal methods is kind of a difficult topic to get into. And really, this talk is supposed to do two things. Provide motivation for using them, and then also basically just giving you a map, somewhat incomplete, but quite good, I think, map of the territory, and then show you a little bit of it in action. So formal methods is a large category of practices. And I think that it's not an arbitrary division to say that most of them in practice will fall under either the specification or verification category. Many of them cross boundaries, but if you look at a tool, you'll be able to see that it's more in one camp than the other. So there are a lot of methods of verification. I should probably say more. Yeah, maybe that's fine. But there's also full versus partial verification. So full verification, when you're basically specifying and verifying a system completely, is very difficult, and that's what people think when they're saying verification is really expensive and requires a lot of expertise. But it turns out that actually applying formal methods to just parts of the system provides a lot of benefits too. And so all of these items in this list here can be in the context of full or partial verification, right? So the first is theorem proving. Theorem proving is if you have been a mathematics student or if you studied philosophy, theorem proving is what you'd encounter when you're taking logic classes and you have to write proofs, right? But the proofs just happen to be about programs in this case. And typically what will happen is when you write the proof, you usually write them with proof assistants who will help you come up with the proof and then see if it's right or not, okay? And so it's this theorem proving, you're writing proofs to prove theorems, and and you either wrote a proof that is valid or not. Model checking is a more popular method because essentially what you're doing is you're writing what should happen, you're specifying the results and all of those types of things, and then the software you're using to write this in will actually explore all possible states that the system you specified could be in, and then it will attempt to find one that's wrong. If it doesn't find one that's wrong, then basically you're right. And in another sense, you could also say that model checking attempts to find a counterexample to the claims you've made using logic. And if it can't, then it's saying that you're right. And in model checking, unfortunately, as the complexity of what you're specifying or proving grows, there's this problem of state space explosion, where the number of states your system could be in basically exponentially grows. And in that case, it becomes untenable to try to solve the problem and find counterexamples. In that case, you would perform partial model checking, which will check to a pre-specified number of steps or state changes that your system could perform, and see if within that limited set of steps, does your system follow the rules that you've specified. Constraint solving is another one. And constraint solving is basically, it's interesting because as you're actually writing your code, in practice, this is how it's like, is as you're writing your code, you're actually defining logical constraints, and kind of like how you would add comments to your code, you add these constraints to your code, and then it's basically under the hood, essentially performing model checking is the way you could think about it. Essentially performing model checking to see if your code if your code follows those constraints. Type checking is probably, in my opinion, the least pleasant to use, because you essentially have to use a type system that makes use of something called the Curry-Howard correspondence. And basically what this means is that by typing your program correctly, that itself ensures that it's correct. So you might have heard the term correct by construction. That's what it's referring to. And not every language has some type system, right? So these are specialized proof-based languages that you use here. And then finally, abstract interpretation is essentially almost like testing, very similar to model checking, but it's not really as popular as some of the others. But I put it there so that you know kind of what the topic is about if you come across that term. So I mentioned that there's that division between specification and verification. So specification is, you're basically just describing what the system does. And that's actually what we're going to more cover today, is formal specification, because informal specs abound, and they actually, sometimes you can write what seems like a perfect informal spec, and it turns out to be wrong. Because say you implement it, and maybe it's very simple, and you implement it, and you know for sure, it's simple enough that you can know for sure that the implementation meets the specification, and something's wrong still. So formal specifications use math instead of something else to describe how the system should act. Verification basically takes something as input and checks, does this something implement the specification? So it takes a thing and a specification as input. You can think of it that way, and then spits out a true or false. Does this correctly implement it? It's a mental model you can use. So specifications can also be of specifications. There's no rules about the level of abstraction at which a specification should be written. And so a great example of this is you can specify a particular sorting algorithm, such as quicksort, as well as a specification that all sorting algorithms must achieve. And then you can check, does my specification of the quicksort algorithm comply with the specification of sorting algorithms? And what is something that all sorting algorithms must do? Well, they take something that's ordered or unordered, a list, and outputs an ordered list. There's a typo there, but that's supposed to say ordered. So given that specification of all sorting algorithms, well, I could also specify quicksort, one particular sorting algorithm, and check, does quicksort meet the specification? So now we get to we've gone over the why and the what, so now the how. And there are so many tools, but I want to focus on one that's had a lot of industry adoption, and it's Tla Plus. And the reason it's had a lot of industry adoption is it's built with practitioners in mind. It's not built for theorists. It has a low barrier of entry. There's no type theory, which I mentioned before. Type checking is one way to do it, but it's not based on type theory. And if you just Google Leslie Lamport, essentially, you'll come across his website. And he has some great articles on his blog. And one does talk about the trade-offs between using a type theory versus elementary math, and why he chose to go with elementary math for Tla Plus instead of a type theory. I highly recommend looking into it. I use Tla Plus in my work, and some of my colleagues also use Tla Plus, and it was quick onboarding, and it has helped immensely, which is why I decided I might want to do a tech talk about it. So yeah, so Tla Plus, it's used for specifications, not for verifications, right? So you use Tla Plus to ensure that you understand how your system should behave. And if you do start using it, you will amaze yourself at how even a simple system, which we'll even cover today, how you do not understand it as well as you think you do. Tla Plus is the tool that was mentioned in the article about Amazon Web Services, that article I mentioned earlier. They were using Tla Plus. Other companies use Tla Plus, such as Intel. It's suitable for anything from hardware, specifying hardware, all the way up to distributed systems. Interestingly, there's this other thing, this other language, if you will, called PlusCal. And PlusCal is basically a mathematical replacement for pseudocode. And it's in the Tla Plus ecosystem. Oh, and by the way, Tla Plus stands for the temporal logic of actions. So it uses a form of logic called temporal logic, which basically allows you to specify things called safety and liveness properties. And I won't get into that, but just so you know what that is, we'll see a bit of temporal logic today. Anyway, so PlusCal actually can be automatically transformed into Tla Plus, and it's even easier than Tla Plus. So basically, you're used to writing pseudocode probably, especially here because of the PDAC process. This is a replacement for that, for pseudocode. And one core idea you'll find in formal methods in general, especially specification, is that it's it all boils down to a single formula, a logical formula. And that formula is a function that maps possible behaviors as inputs to Boolean values. And a good specification maps the behavior of the system to the Boolean values such that any correct behavior that's used as input to this function outputs true. So any incorrect behavior, this logical formula will output false, and any correct behavior will output true. Okay, so that blank slide indicates that it's example time. So I have Tla Plus toolbox here, and you can download that online, just Google it. And we're basically going to create a new specification here. And I'm gonna go over today something that you'll see in one of the books. If you just Google, let's say practical Tla, there's quite a good book about it. Pretty light reading, but very, very informative. And I'm going to kind of use an adapted example from one of those books because it really highlights how you can misunderstand a very simple system. And this example is going to be about wire transfers in banks. So we're just going to do wire transfer. So this is what you get when you initially create a new specification, and I actually forgot what I was about to say. I swear I had a good comment. Anyway, we're going to talk about wire transfers. So what does this mean? Well, in this simple example, we're going to use basically have a system set up where one person transfers money to another person. And to start, and we're actually going to do this in PlusCal which is kind of the special pseudocode that compiles the Tla Plus. So in PlusCal, we use that syntax to start the actual pseudocode. Okay, and we want to specify an algorithm for transferring. So we'll type algorithm there, and then we're just going to do the name of the algorithm, which is wire. And in this example, we have two people, and we want them to be able to transfer money between each other. So we have two different pieces of state. We want to think about what is the state that we want? What's the state of our system? And we'll put those in variables. So you see how this is a nice environment because specialized reserved keywords are highlighted in red or colored in red. So variables, which is we can specify the state of our program. So for that, well, we need two things. If it's people transferring money, we need people. I'll call them Joe and Jennifer. So those are our two people transferring between each other. And then we also need that people have balances, right? And we are very familiar with this notion of an account, right? So do account, and this is a syntax we use. We basically write set theoretic function inside square brackets. So we'll say that an account is a mapping for every person. So for each person in which, if you're familiar with set theory, that kind of weird E looking symbol for is an element of. So this is what this is for. So, and we can actually compile this or output this specification when done as a nice looking formula. So for P in people, such that this is, you can read that symbol as such that 5, right? Let's just say 5. So that's so basically we're saying that the initial state of our system is we have these people, And for each person in people, we're mapping this is a function that takes a person and outputs 5. Okay, and actually it's semicolon sensitive here. So what's the next thing we want to define? Sorry, can you increase the TLA window font? Yeah, I think so. Maybe if I do Command plus, that'll do something. Do anything. So TLA plus, you can kind of see that it's kind of an old tool. That doesn't do anything. I don't see how to. I'm sorry about that. Maybe in the recording it'll be better because you can full screen it yourself. But okay, anyway, so we have the initial state. Now, what's something that you basically can't do with money? Ideally, is you can't double spend it, right? So basically, we need to define some sort of rule that should always hold, an invariant, if you will. So we're going to use the define keyword for that. We're just going to say positive balance. And for these, we use these double quotes. Usually we say these are equality, but really in PlusCal and Tla Plus, these single quotes, you can set a variable's value. These double quotes, you can think of the single quote as saying variable count is assigned to this. These double equality signs, you can take that to mean in English as this is defined as whatever we put there. So that's what that is. And basically we need to make sure that for all people, their balance is greater than or equal to 0, right? So just like there's the in keyword for the is an element of set, because this is just using basic math and set theory, this symbol right here means for all variable in people, and we can access things like Tla Plus gives us nice ways to, as programmers, we're used to accessing, say, hash tables by key. We can add things, we can access things like this pretty nicely. So we can just use the P in people is greater than or equal to 0, right? And define. Okay, so we'll actually do something else here. We have our rule set up. We have our initial state set up, but what's the actual algorithm, right? And we're actually going to do something interesting where we're going to have, what if we're going to think about, and this will highlight how good Tla Plus is in distributed systems like concurrency, is we're actually going to define multiple executions of this algorithm that happen at once. And we want to make sure, because otherwise it's quite trivial, right? We want to make sure that no matter what, even if they execute multiple wire transfers at the same time, we want to make sure that basically this always holds. So we do that with the process keyword, which defines basically this abstraction of a parallel executing process. We'll call it wire. And we need more than just one of them. So just like before, we'll say in, and we'll just do 2 of them. And this, you're familiar with this, that defines a range. So each process has its own initial state as well, right? We have the entire system initial state and the process open state initial state. So we got to define our variables in here as well. We'll say sender equals Joe. and receiver equals Jennifer. And the amount is non-deterministic. The amount that Joe sends to Jennifer is non-deterministic. And it's perhaps the case that if Joe sends one particular amount to Jennifer, that the algorithm works, but another amount, then it doesn't. So we're actually going to define a set that amount can take as a value. And in doing that, when it's executing, Tla Plus uses a model checker behind the scenes. Tla Plus will ensure that regardless of what amount is, the constraints hold, right? The positive balance rule holds. So we'll say amount in, and we'll do a range. To account, and we'll check the account of sender. So they can send any amount, right? Now, when we want to actually write the steps, well, we need to use some sort of looping, and that's uses the begin end keywords. So we'll say we want to define basically a withdraw and a deposit action, because to transfer to one person, you have to withdraw from your own account, and then the money needs to be deposited to the other person's, right? And the reason why we would do this as two separate actions is because basically, well, you can't update them with the same statement, right? They're different operations up in because they operate on different states. So that's why we would do that. And this just takes some intuition to build up. So we'll say account sender. And when we want to reassign something like this, we use this. And if you're familiar with pseudocode, this is often, this colon equal sign is often a syntax that's used for setting variables to a particular value, especially with reassignment. So we'll say account sender, and what do we need to do with a withdraw? We need to do account.send. We need to do the original balance minus the amount, right? Also, since these are variables, they probably need. I just realized I did that too. Okay, so we have withdraw, and then, you know, another interesting thing here is that if you're familiar with Python, this type of indentation-based syntax is familiar to you. So then we also need deposit, and here we want account receiver to equal the amount, basically, of previous amount plus the amount that's been sent, right? Want to basically end the process there. And then you also need to type end algorithm, okay? So I think that it might be good to ask people now, what do you think about this? Does it make sense? Is there anything confusing so far? And do you think that this will work? Okay, well, nothing so far, but I'll say that I tend to think this will work, right? I mean, we're just having our people with our accounts, and I mean, when you withdraw and send, you make sure that you decrease the amount before you deposit it somewhere else. Seems fine to me. So then what we will do is we'll go to wasn't going to follow. Okay. What we'll do is we'll translate this PlusCal algorithm to Tla Plus. So this will, because remember, PlusCal is even higher level. It's just pseudocode, and we're going to translate it to Tla Plus. So let's see. Okay, I have an error here. Probably. Okay, I didn't need the semicolon there. I also realized I have another mistake, which is we're using plus and minus to talk about actual numbers. And so we actually need Tla Plus needs to know what we mean. So we say extend integers, because we could be talking about, say, matrices. It doesn't know what we mean when we use arithmetic or subtraction operations, for example. So let's try again. Okay, and as you can see, the output here is this whole thing, and this is Tla Plus. And mostly I've written Tla Plus like this, but when I started using PlusCal, I realized it's much nicer, right? So that's what I did. Okay, so now we have our algorithm, right? We have the rule that it should always follow. We also now need to check that it's actually correct. So we're going to put a new model here, and we'll just say transfer. We're going to basically uncheck deadlock. And in variance, we want to add this positive balance rule. Otherwise, I won't know to check for that one. And then we just press this to check the model. And it's running, it's testing all possible states right now. Okay, and we notice that it's not working. Let's see what the error was. Okay, it says here that our positive balance has been violated. And we can step through this right now, is that we see that we've been, during the initialization of the withdraw process, we have Joe's balance set to 0 and Jennifer's set to 5. Right? And then what we're in the first process is 1, the second process is 5, because remember we're doing multiple processes. But then when we execute, goes down, goes down, goes down. And we see that Joe has reached a -1 in his balance. So he's basically overdrawn. So the most obvious thing to do here is to basically check that before withdrawing, that the sender has enough to withdraw, right? That makes sense to me. So we can do that here. We define this procedure called check funds. And we say that if amount, right, is less than or equal to account sender, then we can do this, right? If it's not going to cause them an overdraft, then we can do that. And then just like in classic pseudocode, it's an if and an end if. So let's try that. And once again, we'll want to translate to PlusCal. Expected then, oh yeah. You need to put a then after an if clause. Whoops. Okay, so it's successfully translated the algorithm. This is not, it did not just run the model again. That's from the previous, that pain's from the previous run. So we're going to rerun it now. Okay, and this also fails, which is pretty crazy. And I mean, let's see why. So we start with them both having a 5 for a balance. Okay. And then we'll have 5 again. We have withdraw and check funds. So it's within the withdraw stage. We just kind of step through all of this. So at some point, we have Joe has a balance of 4. Yet, on the very next state, the very next withdrawal, he has a balance of -1 again. And you can see here that before, I don't know if you noticed, but this queue size was 56 and now it's 122. So it took 122 tries to find the issue, which is pretty crazy. Like, why would this, if we always check if the amount is less than or equal to the sender's balance, why would that ever happen? Does anyone have any ideas? Okay. Well, the reason, oh, there's maybe someone has an idea. I just saw chat pop up. Race conditions, exactly. So Thomas says race conditions, and that is exactly right. Remember that there are 2 processes executing here. It could be the case that during check funds, so one person, the first process has initiated withdraw, right? But then the other process also initiates withdraw. So say like there was Joe had a balance of 2, and each process wants to withdraw 2. Then we see that they both check this at the same time. So then they both try to withdraw at the same time, right? And so although this seems like it should completely work, it doesn't, because Tla Plus is showing us that, oh, this is vulnerable to a race condition, and race conditions are notoriously terrible to work with and to track down why something was caused. And if you had tried to implement this algorithm, even in something easy like Ruby, you would see that you could not rely on this algorithm. If you ship this to an employer, say a banking or something, people would have issues. So, okay, we know it's a race condition. How do we make this different? Like, what should we change then? Any ideas? Okay. Well, I'll tell you something about Tla Plus, is that it says basically, well, if this amount is less than or equal to sender, then this is a valid operation, or this is a valid operation. Okay. Someone in chat. Yes, Thomas says again, race conditions are non-deterministic. We don't know when they could happen. That's right, because it all depends on the particular execution of that particular path, given the particular conditions. So this syntax in Tla Plus basically says, or sorry, PlusCal, basically says this is one path, one operation you could do, and then you could also do this one. What we need to do is ensure that basically makes this check for balance atomic with the withdrawal. So we need to make sure that every time this occurs, every time this check occurs, it's immediately withdrawn. Okay. And what that will do is that will ensure that basically a process can't check and say, okay, yes, and then say, okay, now I'm going to go down the withdraw path, things like that. So what we're going to do is we're just going to remove this as a possible step and say that always you will withdraw. Anytime you're checking the balance based on the balance of the account based on the amount, if you're checking the balance, you are going to decrease that balance. And hopefully that will work. So we're going to retranslate our algorithm. We translated it. Whoops, I have no idea what I just did. Okay. And then we'll try to rerun it. And hopefully now no one performs an overdraft. Okay, so basically, if it runs and doesn't produce that error output, there are no errors, that means that it passed. So now we found a way that to solve this problem, we just make sure that absolutely every time the balance is checked, it's immediately withdrawn. The balance is checked against the amount is immediately withdrawn from that balance. So when one process checks the amount, before the other process can access the balance, it's already been mutated by the first process. And that way they can never see the same, they can never both see the same balance. And that is, now we can be more confident in this algorithm. And now we also understand it better, and it will be easier for us to implement in actual code as well. Okay, so that's basically all I have about formal methods. We've gone over why we want them, kind of the map of the territory, and we've looked at a very cool tool that takes very little time to learn and then apply to your actual work, which is Tla Plus and PlusCal. Feel free to also ping me in Slack if you want to check out some of these resources or be pointed in the right direction for PlusCal and Tla Plus specifically. I'm a big fan of Tla Plus driven development, if you will. So I will take any questions now, if there are any. So the question is, for a launch school student, when in our learning process does it make sense to experiment with these tools? And basically, I would say that this is something that becomes more impactful once you finish core. However, having said that, I believe that PlusCal specifically complements the PDAC process very, very well, because the whole point of the PDAC process is to make sure that you understand the problem well and then understand the solution well. And so that is exactly what Tla Plus and PlusCal are for, right? I wouldn't say that you absolutely need to make sure that you learn this, so don't put that type of pressure on yourself. Many developers go their whole careers without ever getting into formal methods. Formal methods make more sense in some domains more than they do others. There's another one, but this might sound silly, but what's the best way to convert from Ruby into Tla Plus? Or should it start in PlusCal and then translate to Ruby? So remember that, so Tla Plus is the original, and it's a bit more mathematical, not in an intimidating, sophisticated way. It's using a very simple math, very fundamental math. And you can pick up a book on elementary math, like on set theory and things, and formal and just basic logic, and that's enough prerequisite. And I'm happy to recommend those resources to those who want it. Anyway, once you write it in Tla Plus or PlusCal, you then manually translate it into Ruby, and you hit on, and this was asked by Lee, you hit on a very good issue, which is, okay, I formally specified my algorithm and I know it's correct, but is my implementation correct? And that is something that's very difficult. And I'll talk about it, and I'll highlight something. even if you say were to use formal verification inside of your Ruby code, for example, to prove that your Ruby code is correct. Okay, but how do you know that the interpreter is implemented correctly? The Ruby interpreter. Maybe it has some sort of issue in its correctness. Even if the Ruby interpreter is correct, how do you know that maybe it's written in C? How do you know that the C is correct? Or sorry, that would be. But how do you know that the assembler and compiler are fully correct? Even if so, how do you know that the hardware that it runs on is fully correct, right? So at some point, and this is the bane of people in the formal verification space's existence, is at some point you always have to take it for granted that something is implemented properly. Otherwise, you just keep going down. Maybe the laws of physics aren't correct, right? And so Thomas asked how difficult it is to use these formal methods to check a larger app is implemented correctly in a framework. And then he just sort of answered his question. So with Rails or React, those specifically, I want to say something else about them, which is that you would never, it's very rare these days to fully verify a program. What I would do if I was working in Rails or React and it's a system that it makes sense to do some formal methods in, I would specify one particular algorithm. Say I have some sort of scheduling service. I would specify the algorithm used by the scheduling service. And that's perfectly fine, right? But you wouldn't really apply it to the entire application. I'm not saying that's what you're thinking here, but I just wanted to highlight that more common in industry is to use it for parts that are more difficult, but rarely the whole system itself, because that takes a long time. It's pretty hard. John asks, as a developer, is focusing on building tests or formally verifying your algorithm more efficient? So as a developer, it's very important to think about the how you allocate your resources. And testing is easier. It's easier than formal verification. And it's easier than formal specification. It also lends less confidence. I would trust something that's been formally verified more than I trust something that's been tested. So it really depends on what is more suitable to the system you're building. Like I said, if you're working on critical software, working on financial software or blockchain, it's more efficient to verify and test than it is to focus on one or the other. And if you did have to focus on one or the other, it's probably more efficient to formally verify because the stakes are higher, right? But if I'm just building a to-do app and I decide to formally verify it, well, that's a waste of resources. And if I'm being employed by someone who's paying me and I'm spending all that time formally using formal methods for this to-do app, then they're probably going to think, well, that's a perfect example of over-engineering. You need to learn to manage your resources properly.